Hello, good afternoon, and welcome to the education series on UVC LEDs. Today we are going to talk about surface disinfection, and my name is Raju Randive. I'm the Director of Applications Development here at Crystal IS. What I'm going to do is I'm going to go through the basics on UVC LEDs and give you some of the examples, and then open it up for any questions you may have. So who we are, briefly, we were founded, Crystal IS was founded in 1997 and acquired by a large Japanese firm, Asahi Kasei, in 2011. As you can see on the left-hand side, our holding company, Asahi Kasei, actually has many different divisions, and they do a lot of different things from materials to healthcare, and including homes. But Crystal IS actually falls under their research center and innovation group. So since they bought us, they actually have kept the headquarters here in Troy, New York, which is just north of Albany. We actually have both manufacturing both in US and in Japan. And as far as the sales offices are concerned, we have it all across the globe, US, Japan, China, and Europe. And the biggest thing about the UVC LEDs we make is our sauce, which is basically the aluminum nitride substrates, compared to what other traditional LEDs substrate is being used currently. So jumping right into the what is UV disinfection, basically here is the spectrum. And UVC is one of the C band in a UV region. So when I say C band, typically UVC is defined between 200 and 280 nanometers. So if a light is generated in that area, it would be considered UVC. Once you go beyond 280 nanometers, it falls more into UVB range. I'm not going to go more into details on that. If you have questions, we can talk about it. So how does the disinfection process work? So basically, the UVC generates the photons, which is typically, and it impacts the nuclei of the DNA. So what we are showing here in the left-hand side structure is a DNA of a microbe or just in general a DNA. And it has all the thymine bonds and all the bonds intact. When the photon which is generated from the UVC light comes and hits this DNA of a microbe, what will happen is it will break the bond and form the thymine double bond, which you can see on the right-hand side. So basically, it forming this double bond prevents the DNA from multiplying. So we are not really just killing the microbe, but we are basically stopping it from the further growth. That is basically the process which is used for UVC LEDs. Now, when I say thymine bond, this is typically true as far as the DNA is concerned. But on the right-hand side plot, you can see that there is a difference between RNA, which is viruses, which has a uracil bonds. And the light required is little bit lower than the light that is required for the thymine. So somewhere still in the 260 to 265 nanometer range is what we are talking about. So not a big difference, still a UVC range. So this is the basic idea for disinfection. So let's look at some of the spectral sensitivity of different microbes. So what I'm showing here is 4 different microbes: E. coli, MRSA, crypto, and rotavirus. So these are different types of microbes. So we are talking about protozoa, virus, and bacteria. And what you can see is the absorption spectra or curves for those 4. And what we show here is that somewhere between 260 and 275 nanometer is where you see the absorption maxima for those microbes. So, and that is basically what we consider the germicidal. So we are considering 250 to 280 as a germicidal range. 280 and above is the UVB range. And 260 to 275 is the maxima, and that is where our Clarion product emission range is also. So that actually perfectly attacks the DNA of these microbes. So I just showed you four different microbes, but if you look at a lot of different microbes, which was actually an article published in IUVL News earlier this year, it shows, and what we have done is we have highlighted with a red box in this table, the absorption maxima for a lot of different microbes. And you will see that 260 to 270 is, you'll see a lot of yellows, which are the highest peak for those microbes. And that is a perfect range for getting the maximum absorption. And so the Clarion product we have works really well in that particular disinfection range. So why is the UV disinfection important? So this is well understood, and basically the UV cannot be overdosed, no byproducts, no organic compounds. You don't need to do storage of the hazardous material. And what I'm referring to here is this materials like chlorine, which is also used for disinfection. The requirement is minimum in terms of equipment which is required. And also, it is very effective with a lot of different, what we call it as the super bulbs. And some of the advantages over Mercury, we can actually do instant on-off, and this is because LEDs is a solid-state device. Instant on-off will not, or multiple on-off cycles will not affect the lifetime of the product. Also, it's a directional emission. So the light coming out of the LEDs typically come out in one direction. The viewing angles range from about 105 to 120 degrees. It depends on the type of product. As far as Mercury is concerned, we are talking about 360-degree emission. So you really have to use reflectors and stuff to direct the light. In case of LEDs, you don't have to worry about that. Also, the power requirements, it's a low DC power, so you can use very simple, inexpensive drivers to operate the LEDs. It is compact package. So we are talking about a package with a size of 3.5 by 3.5 millimeters. So just to give you an idea, if you take a penny, you can put very easily 6 of these LEDs on that penny. So it just gives you a thought process of how compact they are, and you can actually really do a lot of design flexibility with the LEDs. And these are eco-friendly constructions, so that means that you don't have to worry about the disposal, especially compared with the Mercury lamps. Jumping right into dose and microbes. How do we calculate the dose? I think most of you should be familiar with it, but the UV dose is typically defined as millijoules per square centimeter, or joules per meter square is another term you will see. And that is equivalent to the radiance or the power output coming out of the LED divided by the target area in square centimeters. That would give you the intensity, also called irradiance. And you multiply with the exposure time, which is typically in seconds. So you are talking about how long do you have to expose to that microbe. Now, so this is a very critical aspect of it. Is so not necessarily, you don't really need a very high light output device if you have a lot of time in your hand to do a disinfection. So we can really play with this number quite a bit. So when we talk to you about your application and how does the disinfection work, or what you are trying to disinfect, we can use this formula quite a bit in your advantage for designing the product. The bottom pictures you see basically talks about the viewing angle. So what it's showing is that if you are far away from the LEDs, which is shown as H1, you actually can cover a much larger area. But with that larger area, the intensity is going to be much lower based on the formula on the top. But if you are much closer in terms of H2 and it will cover only area A2, so the distance plays a very critical role. And at the bottom, it basically is disinfection level is basically a function of radiance, time, and distance. So we can really use that to our benefit. Here is a table typically of some of the disinfection or the dosages required. And what we have done is we are showing some of the commonly used microbes which are present for the surface disinfection. And the values, the log reduction value of 2, 3, 4, and what is the dosage in millijoules per square centimeter. Now remember, the dosage we are talking over here is based on the 254 nanometer, which is the Mercury lamp. We don't have the database for the UVC LEDs right now, but we have done some work on some of the microbes shown here to see how much dose is required to get to that to the disinfection level or log reduction aspects. Let's look at the power and light function. So what we are showing here is current. The LEDs will be turned on based on the input currents. So the higher the current you put in, the more power you get. Now, one thing I want to remind is that there is a limit on what is the maximum current you get. And the reason is that not all the power you are putting in gets converted into UVC light. And if the power does not get all the current does not get converted to the UVC light, you are going to generate a lot of heat. And the more heat it generates, and the third bullet over here, which is temperature up, you are going to increase the temperature. The more temperature you increase is going to impact the lifetime of the LEDs. So the lifetime of the product will go down. So this is a very critical parameters you really have to think about. And what we are saying is lifetime and power both are the design variables. They are not the absolute values. So playing with this power and lifetime would be another thing we can help you with when designing the product. Here is an example of optical power versus a lifetime. We are focused just on a 250-hour prediction. We are not looking at a much longer lifetime, just for as an example. So the first line, we show that if you use high current, in this case, we are saying let's operate the LED at 700 milliamps. We can get a power output somewhere between 35 to 37 milliwatts. At 250 hours, we are going to have approximately 32 milliwatts of power coming because we are degrading the LED at a much sharper rate. But if you don't want that much power, but you want a much consistent power, you can operate it in a normal current mode, which is a 350 milliamp. It will basically start at approximately 22, 25, depending on the LED. But you can see that the slope is very less steep, and the power output will be still higher than 20 milliwatts after 250 hours. So depending on the lifetime requirement, you can actually play around quite a bit with the intensity or the power output versus the lifetime. And you see the big difference when you go to much longer lifetime hours. So if you compare 1,000 hours between the two, high current and the normal current, a high current product would have dropped from 37 milliwatts down to almost 18, 19 milliwatts. But a 22 milliwatt product is only gone down to about 17, 18 milliwatts. So there is a big advantage of using a normal current or 350 milliamps of current for that long life application. So again, this is something where we would come into picture and help with the design aspect. Very key parameter, we talked about the temperature. So one of the big advantage of the LEDs is that the light is coming out on the top and the heat is coming out on the back of the LED. So you can actually control the temperature of the LED really well. By putting in the thermal paste, the heat sinks, maybe put it on a PCB and then put a heat sink associated with it. And then depending on what currents and temperatures you are operating at, you may need some kind of active or passive cooling. You can see on the left-hand side what happens with the lifetime. So if you have a much lower operating current, what we call junction temperature, which is very critical aspect of the LED, the lifetime is really high. We are talking about close to 15,000 hours. But as soon as we start increasing the current, the junction temperature would go up, and the lifetime would go down. And we are talking at 115 degrees of junction temperature. Our lifetime is somewhere in the 6,000 to 8,000 range. Again, it will depend on type of the LEDs and what the application is, and we can play with that. So doing some of the design consideration aspect. So I had mentioned UVC source. It's a one directional or a directional emission pattern. So you can put the UV source on one side and basically use the target area for disinfection as shown in the figure. So some of the things you need to really consider for your design consideration would be size of the area you want to disinfect. What is the finish of the surface? And what I mean by that is if you are going to disinfect a very classic example would be an apple surface versus a cantaloupe surface. Apple surface is pretty smooth on top. Cantaloupe has lots of nooks and crannies. So trying to disinfect cantaloupe would be a lot more trickier than apple. And the reason is that the nooks and the UVC disinfection works with line of sight, and your line of sight for cantaloupes would be very different because of nooks and crannies. So that is what I mean by finish of the surface. One of the things we talked about earlier was the distance from the light source. So the much further away you are, you will need a much higher power output LEDs, or you can control it with the next design consideration, which is the exposure time. The concerns you need to really think about is the uniformity of the irradiation. So you can put a LED source much further away, but the center of that contact area will get much higher light output. But as you go away in that circle you see, the edges of the circle will get a little less light. So you will have to worry about what is the uniformity over there, and consider that as a lowest irradiance point, and then do all your dosage requirement calculation based on that. You need to think in terms of time at disposal. And then finally, health and safety, because if you're trying to disinfect a room, you cannot have the LEDs on when people are there. You just have to make sure that the LEDs are turned off, or the UVC LEDs are turned off in presence of people. So that's what you need to worry about. Over here, we are just looking at here we are looking at just one example for balancing the goals for MRSA disinfection, and we are looking at two different distances, a distance of 2 inches and a 3-inch distance, and we are also looking at a log reduction on the y-axis and time on the x-axis. And what you see is that around for 2 log reduction at the 2-inch and 3-inch is not a big difference at 15 seconds. But as you go higher in time and more log reduction required, the difference between the 2-inch and 3-inch starts to show up. At 60 seconds, you can see that you can get to 2 log reduction at 3-inch distance, but very close to 6 log reduction at a 2-inch distance. So that's almost 2.5, 3 times difference between the two different distances. So distance would play a very critical role. And again, this is the experiment we had done using our LEDs with a third party. So now I want to show you a couple of the examples of what are the variable we had spoken earlier about, the sources, surface over here. So what we are showing here is a ray tracing. So we take our LEDs and we can place the LED at a certain distance. We know the viewing angles, so we can actually do the modeling based on that. So we are taking 3 different distances, 20 millimeter, 50 millimeters, and 100 millimeters. So the distances between the surface and the LED source. And based on our modeling, what you can see is when you are at a 20 millimeter source, a 5 by 5 area basically shows a very clear or very distinct LED pattern. And it shows exactly how the 4 LEDs are located on that for doing the surface disinfection. We can also look at what is the minimum UV intensity, and the minimum UV intensity is at the corners, which is 0.01 milliwatts per square centimeter. Now we go away from moving further away, and at 50 millimeter, we can see that you can still see a little bit of a pattern, but it's starting to get a lot more uniform. And still, again, there is a minimum UV intensity which is present at the corners, and we are talking about this time 0.09 milliwatts per square centimeter. But you can see just by going away from the distance, by going away from the substrate or your surface, we have increased the minimum UV intensity from 0.01 to 0.09. Of course, we have decreased it in the middle, but again, uniformity is a very critical factor, as we had seen before. Now you go at 100 millimeters away, and you can see that the uniformity looks much better, but the intensity in the corners have gone down, and now we are looking at only 0.04 milliwatts per square centimeter. So we actually would work with you and help you design based on some of this modeling work capabilities we have here at Crystal IS. The other thing we want to look at is keeping that surface as the constant, but changing the number of LEDs. And what we are doing is we have looked at 1, 3, and 4 LEDs system. And again, you can get the LEDs with one LED. You can get a certain intensity, and it is only 0.01 milliwatts per square centimeter again. And you can see that uniformity is really well, and you are getting a pretty good intensity at with 0.09 milliwatts per square centimeter with 4 LEDs. So we would work with this also to figure out what is the impact of LEDs on the uniformity. And then, of course, the last one in the variable column is the optical power. So we have different LEDs, and you can find this on our website. And the difference between the Clarence P, Q, and R is basically the power output. And what we are showing here is not necessarily the highest powered LEDs is the best solution for you. We feel that in this case, the Clarence Q, which is the second highest power, might be a better solution depending on the microbe we are trying to disinfect. So I want to just use that and show you one case study and then we'll open it up for questions. So let's say if we are trying to do 4-log reduction of Pseudomonas, which requires typically 22 millijoules per square centimeter. And what we are doing is basically doing the disinfection requirement at end of life of the LED. And what would you define end of life requirement? So in this case, we say that I have a product maintenance cycle which is 1 year. The LED is on maximum 10 minutes a day, so which is approximately 60 hours. So we are looking at basically 22 millijoules per square centimeter, which needs to be delivered after 60 hours of life, not at the beginning of the life. So not when the LEDs are brand new, but LEDs when they have been operated. So we would go through this the whole design cycle, the surface size versus the distance, number of LEDs which is required, and based on all this information, we can basically say that you have X amount of time which is required. We would say that you require 15 seconds per day to get to this. We have also looked at 3 different surface areas, 5 millimeters, 10 millimeters, and 50 millimeters away. And we did the calculation and said that in 15 seconds, you should be able to get to the disinfection level you are looking at, based on our 25 milliwatt LED, which is our Claren Q LEDs. So with that, I would like to thank for your attention and open it up for any questions. So one of the questions is related to the price point of the LEDs. So it's an interesting question. What I would say is that there are a couple of different things. It will depend on the application and the power output you are looking for. It will also depend on the volumes. And we can definitely work with you on your application and the volumes you have to come up with the prices. But again, the LEDs prices have come down drastically in recent times, and you should be able to find the LEDs at a much lower cost. So the other question is what voltage sources are required. So we typically suggest our customers to use a driver, which is a constant current driver. Per LED, we are looking at less than 10 volts. Typical values are somewhere around 8.3 volts when you drive it at 400 milliamps. Can you explain the difference in the scale on your irradiance plot? Scale of the irradiance plot. I'll just take this one. So one of the things is, it's a great point, and one of the things we are trying to do is to come up with a uniform way of doing it. The radiance scale basically is defined by our software. Basically, and it's just a artifact in the sense that each one will be different. So if you look at this page, you can see that the top one, when the LED is very close, we have a red mark over there where we are getting a very high irradiance. But as you go away the center is still higher, which is at 10.8 milliwatts per centimeter irradiance at that area. But one of the things we have been talking about is the irradiance we are interested is towards the edges. And in the first one, the edges is very close to between 0 and 3.6 milliwatts. As you go a little bit below, it goes from 0 to 1.1 to 2.2 milliwatts per square centimeter. So this is just an artifact as far as the plots are concerned. Page 21. So the other question was related to page 21 on the irradiance plot, and again the same thing. It's based on the scaling, and I think we need to do a little bit of our own homework and change this plot to put all the scale factor in a similar way, so that all the scales are similar. But this is just showing where the maxima is based on the color. So the question was again going back to this plot where we are showing that that the time factor is similar, 15 seconds. So this is based on the minimum UV intensity. What we are showing, the minimum intensity remains same, so the disinfection level will remain same, which is 15 seconds. If the minimum intensity change, and as you can see from our 5 millimeter array that there was no minimum UV intensity at the corners, you cannot really disinfect. So that's completely based on the minimum disinfection level. So there is a question related to the safety. So in terms of safety, in general, UV source, you need to worry about the skin and the eyes. Overall, the UVC light will only will not penetrate through your skin. So typically, wearing some kind of a safety glasses and gloves should be enough when working with the LEDs. The concern comes in terms of patients in the room when you are doing the surface disinfection is related to the amount of time a patient could be exposed without any kind of a protective gear. And there is a ACGIH has some limitations on the exposure time. And we can definitely share that kind of information with you if you have any concerns or if you need to look at that. If you have no more questions, I would like to thank you for your time and attention. And if you remember or if you come up with any questions, feel free to get in touch with us. And last thing, I would like to also let you know that you'll get a email with our link to our presentation, and also we have a closed, basically invite-only LinkedIn group, what we call a UVC LED disinfection community, where you can actually have this conversations about the UVC LEDs. not only with us, but with our other invited guests over there. So please join that, and you can ask us any questions over there, and we would get back to you. Thank you for your attention, and hope to talk to you guys all soon.